Okay, shall we get started? So the last hour, we look at two evidences of the cosmic microwave background, right? The first one is actually very simple, expansion of the universe. If the universe is expanding, we rewind the clock, the universe is smaller, and it goes back to the Big Bang. And the second evidence, we look at the cosmic microwave background. Cosmic microwave background is uniformly coming from everywhere with the same very uniform temperature. So that can be explained if the universe is started with a very small Big Bang, as described in alpha, beta, gamma theory. So these are two evidences of the Big Bang, right? And then now we're going to look at the third evidence, Big Bang nucleosynthesis. And then this chapter, you realize that these basic elements of the universe are formed in 1,000 seconds. Basic elements like hydrogen, helium, lithium. Most of the basic elements formed in only 1,000 seconds at the beginning of the universe. So that's what we are going to look at this now. Okay, let's get started. So last time we looked at this temperature of the CMB scale with 1 plus z, right? And if we rewind the clock, that means going to higher redshift, larger z, then universe becomes hotter and hotter and hotter, right? Then you might wonder, you mentioned that 3,000 degrees, right, universe. And in such high temperature, it's very similar to sun's temperature. So there may be a nucleosynthesis happening in the universe. You might wonder, in such high temperature. And it did happen. It did happen. But it's a little bit different from sun's core. Sun's core is matter dominated, but universe at this time was radiation dominated. So it was a little bit different. And there's one concept very important in this picture, the chapter, is freeze out. So I want everybody to understand what is freeze out before you go out of this room today. Okay, so you cannot go to bathroom before understanding freeze out. Okay, so Jaya. Okay, let's get started. So let's think about thermal equilibrium. So in a very hot universe, the universe was very small, right? And this collision time scale was very much shorter than the expansion time scale. So the universe was in thermal equilibrium in high density, high temperature. Okay, and then in such equilibrium, distribution follows Boltzmann distribution. Okay, then the number density ratio of neutron and proton is going to be followed. This is Boltzmann distribution. This is Boltzmann distribution. And then you put the numbers like K Boltzmann constant, and then the mass difference, speed of light, and it becomes something like this. And this T is the temperature of the universe. And mass difference between neutron and the proton is something like this: 1.25 mega electron volt per square c square. And then in this equilibrium, this kind of reaction is happening. Okay. So the proton becomes neutron, and then neutron becomes proton, and then another one, proton, and the anti-electron neutrino becomes neutron plus anti-electron. So this kind of reaction was going back and forth, and then following this Boltzmann distribution. So that's what was happening, in the early universe. Proton was becoming neutron, and then go back and forth. This happening. And then the reaction rate B is actually decided, this is from weak nuclear force that we are not going to go into, but I was following something like this to the -5 per second, something like that. Okay, then in the early universe, so that was happening. Now we want to see the reaction time scale. So what's the time scale of this reaction? Okay, this reaction time scale. What's the time scale? We are going to look at that next. And then, okay, the early universe, the CMB temperature follows this. That's, we already look at it. And then omega curvature can be almost zero in the early universe. In the early universe, cosmological parameters are dominated by radiation. So we don't need to think about curvature. And then radiation dominated universe, it scales with scale factor scale with the t to the square root. This, we didn't do it, but it's exercise 2.4. This is kind of important, so if you have time, please look at the exercise 2.4. But we skipped it, so just trust my words, you know. You trust me, right? It's going to be like this. Okay. Then, so now what is going on? And then the scale factor is going to be proportional to square root of t. So that means t's time is proportional to scale factor square, and the square factor is this, right? 1 plus z inverse 1 plus z, so inverse 1 plus z, inverse 1 plus z. And then this 1 plus z is related to the temperature, so it's like temperature minus 2. Okay? And then, okay, then what we derived here, okay, then so the important point is this t, reaction time scale is proportional to t minus 2, which is here. And then you put instead of proportional, you put a lot of numbers, then you have some constant here. Okay? And then, but the important thing is this temperature scale with time minus 2. Okay? Then reaction time scale, now that this is a relation between the temperature and time, right, of the universe. Then reaction time scale is, as we saw, it's Boltzmann distribution. So this t to the minus 5, temperature minus 5. Okay. Of course, if the temperature is higher, reaction time scale is shorter. If temperature is lower, time scale is longer because it's minus, right? And then we put here small t, which is time. Then it's minus 2, so there's minus 2, right? Okay. And then you can see this is time to the power of 2.5. So reaction time scale gets quickly become longer as the universe ages as a function of time. This makes sense, right? Universe is expanding, so if you expand, temperature goes down, reaction time scale becomes longer because it's lower temperature. Right? Then we can think about it. Then age of the universe is, of course, t, right? T is the age of the universe, this small t. And then when t, age of the universe, becomes reaction time scale, then after that, reaction time scale gonna be longer than the age of the universe. And then what happens? Then reaction never happens again, right? Because reaction takes more longer than the age of the universe. Say, for example, if you have a homework that takes 100 years, then you can never finish, right? Age of the universe, it's the same thing. if the reaction takes 100 years, then universe or you students cannot finish it. So when does that happen? Let's see. Then it happens when after this time, after reaction time scale becomes the reaction time scale of the universe. And then, before calculating, so at this point, this reaction between neutron and a proton going back and forth stops. And that is what's called freeze on. And at that point, this ratio, neutron and then proton ratio, is going to freeze out and it never changes because there's no more reaction. So that's called freeze out. And then let's calculate when this happens. So we can just calculate T equal reaction time scale, and then we can calculate when this happens, right? Then the answer is something like it happens when temperature. If you solve this equation for T temperature, and it happens temperature is 10 to the 10 Kelvin, so it's still extremely high temperature, 10 to the 10 degree, right? So what is this? This 10 billion degrees, 10 to the 10, right? So when 10 billion degrees, there's no more neutron-proton reaction happens. And then, at that time, a ratio, following that Boltzmann distribution, ratio of neutron and a proton is 0.34. And then about T is, age of the universe is 1 second. So, you know, when the age of the universe is 1 second, when universe starts and in 1 second, the temperature goes down to the 10 billion degrees, and then neutrino-proton reaction stops, freeze out, at the ratio of 0.34. And then this is the ratio we still have today. So in average, in our universe, the ratio of neutron to proton is this ratio.
How do you do?
You can measure. You can
what?
measure absorption lines,
Oh.
and then you can calculate the ratio. I'll show that later. And actually, this is a very simple argument, but then actually you have to consider a more realistic situation, because transition, it takes time. You know, temperature goes down gradually. Right? Temperature doesn't go down immediately, which we assumed here. So actually, if you calculate a more realistic situation, then the proton to neutron ratio is 1/7, which is actually observed rate. And this is what this George Gamow discussed in his alpha beta gamma theory. This is Big Bang nucleosynthesis, that his paper. This is actually following his paper. Okay, then reaction follows. The next 100 seconds. So now the first one, we only look at the first one. So neutron to proton, proton to neutron, this stops in 1 second, right? When temperature goes down, freeze out in 1 second, and then decides the ratio. And then when the temperature goes down and then down, the following reactions follow. So next, you have this, this kind of reaction, and then on 100 to 200 seconds, deuterium is going to be produced. This is, hydrogen atom that with a little bit, one more neutron, right? Is produced. And then this deuterium becomes hydrogen, and it creates helium, and the helium creates lithium. So these lines, the more and more reactions follows as the expansion universe and temperature goes down. And then at each step, because temperature of the universe is going down as a function of time, right? It's very quickly going down. So at each point, each of the reaction is going to stop As the temperature goes down, this stops, this stops, this stops, this stops, stop. And every time reaction stops, it freezes out the ratio of those elements. So that's what happened in a Big Bang nucleosynthesis. Because this is nuclear reaction, right? It requires higher temperature, so it quickly freezes out as the universe expands. And then, what's amazing is, so here, so that's, if you do the calculation, we're not going to do that, follow these kind of reaction, right? Are you happy? We only did the very simplest one, and we're not going to do the more complicated one. I cannot even do that, so we are going to just look at the result. And then this is the result of the calculation. This is from George Gamown's paper. So this is neutron, right? It freezes out here, right? No. It freezes out here. And then this helium is going to start increase after neutron freezes out. The ratio is not changing, right? And it goes up and like this. And then after helium freezes out here, right? And after helium freezes out, I think the lithium is going to start, right? Producing, right? And then also beryllium, it's also start creating, right? So one freezes and the more heavier ones creates. And then in 1000 seconds here, most of the basic element ratios are already determined, right? Only in 1000 seconds the ratio of the elements of the universe is determined. So I think Stephen Hawking also has a book, right? First 3 minutes that determined that created the universe or something like that. So that book is about this in a very easier way, without using equations. Then, all right. Okay. Then let's compare this. So that's theoretical prediction. What's amazing is this theoretical prediction George Gamow did in 1934, right? And then, many years later, people do the observation and it perfectly agrees. Let's look at that here. So these curves are the same, it's theoretical prediction, right? And then the blue part is observation. And then this actually the number ratio to hydrogen depends on the omega barium. This is cosmological parameter. So this we need to take it from the WMAP measurement. That CMB measurement tells us the value of omega barium. This is also from CMB. This I will tell you maybe in 2 weeks or so. This is amazing information that you can get it from CMB only. Anyway, so this is observation value you take, right? And then you can see this is in a helium value, and this deuterium is perfect agreement, right? Observation on top of the theory, pink. Blue observation is on top of pink theory, right? And then lithium abundance, it's also more or less agrees, right? So this is big triumph. This is called the big triumph of the Big Bang theory, alpha, beta, gamma theory. Isn't it amazing? Like, you predict the number ratio like 30 years before the observation, and then 30 years later, people do observation and it perfectly agrees. Isn't that cool? George, this alpha, beta, gamma theory was created even before people observed CMB. That pigeon's his thing. 30 years before that, he predicted this curve. That's amazing triumph. So this is the third evidence of the Big Bang. So, this element ratio calculated based on the Big Bang theory agrees with observation. So that's evidence of the Big Bang, right? That's supporting the Big Bang happened. Right? Big Bang theory was correct. Okay. Okay. There's a little bit of a difference in lithium here. If your eyes are good, you notice. Because lithium is sometimes destroyed or created in stars, so there may be a little bit of shift here, and it's how much created in stars, how much is destroyed in stars, it's difficult to accurately calculate. But still, so this is actually active area of the research. People are still, trying to, observe and model how much lithium is created in the stars and destroyed in stars, and try to explain this gap. That's still active area of research. Okay, then what's next? Okay, and then also I want to mention a little bit about neutrino. Okay, neutrino also freeze out. This is a freeze out of neutrino. So neutrino was doing this. Anti-electron and electron and then positron was doing neutrino and anti-neutrino. This reaction was going back and forth at the time of Big Bang. But in the same way, when the temperature, this is even earlier, in 0.18 seconds, this reaction freezes out. And then these neutrino should be, becoming like a cosmic neutrino background. So there should be a cosmic neutrino background. That's another prediction of the Big Bang theory. But but this is very, very faint. Detecting neutrino is very difficult, right? Neutrino is going through everybody. Even our body with neutrino go through, right? Even now, well, our body is neutrino is going through. They don't stop from our body, so that's difficult to detect. But maybe in a very far future, if we have very sensitive neutrino telescope, maybe we can detect this. But it should be there. Okay, then. Okay, and George Gamow, you can imagine he was a very humorous person. His title of his paper, name of his paper is Alpha Beta Gamma paper, right? And he wrote a lot of popular science book, like something like this. This is poem Twinkle Twinkle Quasar, and then at the old time they didn't know what are the quasars, right? So Twinkle Twinkle Little Quasar, what are you, or something like that. This is good. This is about Big Bang nucleosynthesis, right? It takes less than an hour to make the atoms, a few 100 million years to make the stars and the planets, but 5 billion years to make human. It's true. Our animals' evolution is much slower than Big Bang nucleosynthesis. And then he also wrote this popular books, The New World of Mr. Tompkins. These books are excellent. So this is Mr. Tompkins. This is a popular science book. It's not a textbook. It's Mr. Tompkins. He travels around in a weird part of the universe. He goes to the, neutron star, and then because of the strong gravity, he cannot wake up because gravity is strong, something like that. It's very unique science book. So it's very unique personality. Okay, maybe I should stop this chapter. Finish here.